Hello, everyone. My name is Yadong. With me today is Yarik. We are from Intel. Today, we're going to talk about SPDK-based IPU storage solutions. Here is a very quick view of agenda. First, we will talk about IPU, DPU storage usages and explain how SPDK can be used to enable each usage model. We will also talk about some of the key SPDK enhancements for IPDP support over the last couple of years, and then do a quick intro of storage management agent, which really helps simplify the integration of IP storage initiators with orchestration frameworks such as Kubernetes. Then we will talk about SPDK and how it plays a critical role in IPDK and OPI projects, and then a quick summary. So here's a very high-level view of IP storage usage models and how SPDK can be used to enable each usage model. I list 4 usage models here. These are very well understood usage models. I'm sure there are many other usage models you can come up with, but I think this 4 covers the majority use case for IPDP storage solutions. The first picture shows NVMe over Fabric initiator usage model. What this picture shows is you add one IPDPU into a computer host, right? In this picture, I'm just using XPU as a general terminology, which covers both IPDPU devices. The XPU, right? In this case, expose one block device interface. We are talking about NVMe as the primary block device interface in this presentation, but you could see some other block device interface such as virtio-blk. So in this picture, XPU basically provides a native PCIe device function, right? An NVMe interface to a host. And then you can freely leverage on the network subsystem accelerators in XPU to do all the storage data path acceleration. But more interesting, you have this very capable SoC inside the XPU. You can run the full SPDK stack, right? So I will explain details in the next couple slides. But basically here, SPDK gives you this software-based NVMe over TCP initiator, just as an example, which you can fully leverage on. And on top of that, you can add a couple IPU, DPU software components to hook up with the device interface, which is the NVMe interface in this picture. So this is a very critical usage model for the IPU DPUs. Enables storage disaggregations in cloud, enables bare metal hosting, right? So this is a very important usage model and very well understood. We will explain more details about software flows. The second picture is similar, but instead of going out to remote for storage access, it actually has a local SSDs attached to XPU. I use this local storage disaggregation as the way to explain this usage model, but you can see many other different terminologies like local instant storage. A good example is actually Nitro SSD from AWS. And so what this looks like is XPU is just another PCIe adapter, right, added into a computer host, which aggregates the SSDs, provides NVMe virtualization, and it comes with all the different accelerators you can use for data path acceleration, for example, CRC, crypto offloads, right? So SPDK can be fully leveraged in this solution as well, which give you this very high performance NVMe driver in user space, and it comes with all the other software components and the configuration APIs you need to provision local storage resource. And then on top of that, right, you can add a couple of software components, just like the first picture, to hook up with the NVMe device, XPU internal interface. So this is another very good example that SPDK can really helps enable the solution. The third picture is basically use XPU to build a storage server. Often it's a simple storage server, so we use this tip-off as the terminology to describe this kind of design, right? It both is just basically just a bunch of flash drives. So you basically see XPU becomes a standalone server in this use case and have SSDs attached to XPU. Often you might see another PCIe switch used to enable fan out, so you can attach more drives. SPDK is a perfect choice in this kind of solution because it gives you all the components you need to build NVMe over fabric targets. For example, NVMe over TCP targets and the NVMe over fabric, NVMe over RDMA targets, right? And it has all the RPC APIs available as well to provision local resource, configure the NVMe fabric target. So it's perfect place for SPDK to enable this kind of storage solutions for IPU DPUs. The fourth picture, which is getting more and more interesting, what this picture trying to show is in a traditional storage server, you add one IPU DP, right, which basically can help accelerate the storage data path. Often this requires software stack, the storage target stack repartition. You basically move some of the front end processing into XPU to make best use of the accelerators, like compression, crypto CRC hash offloads, right? So that's one kind of interesting thing to basically repartition the software stack to make best use of IPU. But this same picture also shows another usage model, which is the HCI, the hyperconverged use case. What this means is if you have like applications, right, like VMs continuously running on storage server, if this kind of application need access remote storage, you can go through the XPU, just like the first picture shows, you can do the initiator in the same picture as well. So now you have both target flow and the initiator flow running concurrently, right? Which is basically the HCI use case. So again, SPDK can be used in SPU, which you can do all the front end processing. So we think that the SPDK really gives a baseline foundation, and it's open source, so you can customize the front end processing as well for different backend storage stack you have. So this is a very high level view. Like this picture shows here, right? SPDK can be used in every usage model here. Really helps enable, IP DPU storage solutions. Just a little bit details about SPDK. So the picture I'm showing here illustrates some of the key software components we can freely leverage on, right? So this picture basically shows NVMe over fabric targets and the layers below that, which includes NVMe over fabric layer, and then this SPDK block device abstraction layer, which is really useful, provide a flexible architecture, right, for supporting a choice of protocols and enable customization. As this picture shows, right, on the BW layer, if you access local drives, you can just go over the PCIe interface. If you want to access remote storage, you can build this, basically use the nvme-tcp, NVMe over RDMA initiators to access remote storage. It also supports legacy protocol like IZZ and Ceph as well. But more interesting, right, you can write your own BDEV and implement your own protocol. Is basically quite flexible. So we think this SPDK, right, really provides a good framework for different IP DPU storage solutions. To give you a little bit more details how we map to the storage solutions we have in IP, right? The first picture shows the GBOF based usage model. This is very simple mapping. We pretty much take everything from SPDK, right, and put it into IPU. Now you can have this GBOF software solution up running. So it's basically pretty much 100% reuse of all SPDK components, right, which can provide NVMe over TCP target solution and NVMe over RDMA target solution, right? Inside IP, what you need is just hook up the kernel networking stack or RDMA, right? With this NVMe fabric layer, so you can build that whole solution. So it's very clean, very simple mapping, and the SPDK is fully used in this solution. The second picture, which is the initiator flow. So this trying to show you another example. Use Intel IPU, previously known as Monavins. The new name is Intel IPU 2100 series, right? So SPDK is fully leveraged in this picture as well. But on top of SPDK, we add a couple software components, which basically enable IPU configuration and get commands from the IPU, right? So which I will explain in next slide. But this is another very good example to show how SPDK can really help enable IPU usage model for the initiators. So a little bit more details, right? If you look at this picture, the IPU DPU works posed on one block device interface. Again, in this example, we use NVMe, right? So if you look at this picture, Monavins expose a high performance NVMe device interface to host. It's a standard interface, so you can use the upstream NVMe driver without any change. Okay, and then once the commands come to the device, this hardware block, the NPI, right, the NVMe protocol initiator hardware block will forward the commands into SOC, and then the software on the SOC will take over. Process the commands, move the commands, do whatever the data processing using QAT hardware block we have in the Monavins, for example, to do CRC crypto, right? Or if you want to do more complex, you can do crypto plus CRC chain operation. So we add basically two or maybe three components here, right? One is NVMe initiator configure driver, which is basically a low-level driver. This is in user space, right? It's basically provide configuration APIs to configure internal hardware block, for example, configure VF, attach a namespace to the VF, right? But it also need to provide the commands processing capability, so that there will be API, available to basically get commands and complete commands, right, to the device. So the commands will go to another very simple software components, API transport. This API transport concept level is similar to TCP transport, RDMA transport in that NVMe fabric layer, right? But the difference here is this API transport is not a networking transport. It's just a local device transport, right? It just enables the access to the local device interface for commands processing and for device configuration. But this model really fully leverage on the SPDK framework, pluggable framework, so makes the integration very clean and maximize software code reuse from SPDK. QAT SDK is just another component that we have to enable that QAT-based acceleration, like for example, crypto offload, compression offload, right? But below the API transport is basically all the software components we talked about previously for the SPDK. It basically includes NVMe fabric layer, BW layer, and then the NVMe over TCP initiator, right? And then go through the kernel TCP stack back to the network interface from Monavins and then go out. So it's very simple, clean flow, which fully leverage on SPDK. The other component that I will explain later is this IPU storage management agent. This is one component in SPDK, which really helps simplify the integration of this whole, IPU initiator with orchestration framework like Kubernetes, OpenStack. I will explain that in a couple of slides. There are many enhancements in SPDK to really help enable IPDP storage solutions. It's quite a bit of effort over the last couple of years. We want to really thank SPDK team for all the great support and the help. I'm just showing a few examples here, right? So we're talking about the API transport integration because it's a local device interface. So there are some changes in the API, make it easy to integrate this kind of IP solution. It really enables a clean integration of this IPU device and the soft components, right? API transport. The second example is IPU storage management, which I will explain in the next slide about this SMA. Really helps simplify the integration with the orchestration frameworks. There's also this auto discovery service added in SPDK initiator side. It really helps enable initiator to automatically discover new namespaces, right, created by the target and automatically connect to the remote target. Helps simplify the configuration flow as well. And then for high availability, the multipath and the asymmetrical namespace support on the initiator side really helps and enable this kind of multipath solution in initiator side. There will be more enhancement coming for sure. I mean, for example, we expect a lot of enhancement coming in the SPDK acceleration framework, which is going to make it easy for storage data path acceleration using different device capability. For example, if you have this chain operation support like Q80, right, which can do compression crypto CRC hash, very complex chain operation, you can use this basically new API to make best use of the chain option, right, to avoid any unnecessary memory bandwidth consumption. So these are the critical enhancements I expect will come to SPDK. And then if you want to do like a new transport offload, for example, nvme over RDMA offload, I expect there will be enhancement in SPDK to make it easy to offload an RDMA QP, right, from the software path to hardware path. So these are examples which will help enable different IP DPU storage offload solutions. So storage management agent, as I mentioned earlier, is just a quick intro here because there's another presentation will go much deeper into SMA design and API level details, right? So what I'm showing here is just at the concept level, this new SMA components in SPDK. Concept level is just one gRPC server, but it's very important because it provides a secure and authenticated configuration channel for IP storage applications. And also it abstracts out low-level details, right, of SPDK JSON IPCs, which is very important because it really simplifies the integration with orchestration framework, Kubernetes, OpenStack, which I will provide one example in next slide. The picture is a very highly simplified view. What this one trying to show is this SMA is designed as a plug-in model, so you can support different IPU DPU solutions, right? In our example, we have nvme interface and API transport. We just need to add the API transport plugin, right, to enable IP specific configurations. But if you support virtio-blk, you can do similarly, just add another virtio transport plugin to enable virtio-blk specific configuration, right, and still be able to leverage on the top level APIs that the IPC calls exposed by SMA to the orchestration frameworks, for example, the Kubernetes CSNO driver. So this is very good design. I mean, quite flexible for supporting different IPU DPU storage initiators. Just as an example, with all the enhancements in SPDK, right? I talk about the auto discovery service. Now the initiator application can fully leverage on that. If remote target create a new namespace and send an AER, right, instant event notification to initiator, now the initiator can automatically discover remote controllers, new namespaces, and then connect to the remote target automatically, right? So you don't need to deal with that in the orchestration framework like CSNO driver. And with SMA introduced, using this Kubernetes CSNO driver example, right? If the API server comes in to say, I want to do a stage volume, it goes to CSNO driver. CSNO driver just call the gRPCs to SMA. You may just need one or maybe two API calls here. The first time you call into SMA, the CS&O driver is going to call this create device API, which is trying to get a device handle. Once you get that device handle, now you can just call attach a volume, right, to SMA, and then SMA will deal with all the low-level details. For example, to figure out do I have a BDEV ready, and then attach that namespace to the subsystem, call into IPU to configure VFs, attach the namespace to VF, right, and all low-level details can be now done inside SMA without exposing exposure to the CS&O driver. So this really simplifies the integration. So now it almost looks like a one-to-one mapping between the CS&O driver gRPC, right, to the SMA gRPC calls. So we think this is a very helpful and simplifies the integration is very important for enable many different IPU solutions. Just put everything together. I mean, we use this example to show all the SPDK enhancement really help enable some true end-to-end software-defined storage solution for IPU. So we demoed this whole nvme-tcp initiator and with backend Lightbits storage service at Intel last year, and this year we showed the performance as well. So is all the enhancement in SPDK, for example, multipath support and enhancement to make it easy for API transport integration, right? And then all the simplified configuration APIs really help to enable this kind of full end-to-end software-defined storage solution for IPU. So we are very grateful to all the great work from SPDK team and the enhancement in SPDK. So that's pretty much come to the first portion of this presentation. So next we will talk about the SPDK and how it plays a critical role in IPDK and OPI projects. So I will hand off to Yarik to talk about more details.
Yeah, thank you, Adam. And we heard a lot about SPDK, and that is a couple additional efforts which are focusing on infrastructure software and infrastructure programming. That is IPDK and OPI, which I will discuss later. This kind of initiative would like to help for simplification development software for IPU, for devices like IPU, and they try to define interfaces for this. But let's walk through over this initiative and understand what and in which one they this kind of things happened. Let's go to next slide. So IPDK, that is a community-driven effort. That is idea that let's we try to define some software framework, target agnostic, and that is focusing on infrastructure programming. And that may be run on any hardware platform. Yeah, that may be the IPU, DPU, CPU on whatever network switch. They focusing on different areas on network, storage, crypto. They expose interfaces up to orchestration. Next slide. So let's quickly discuss about storage on IPU in terms of IPDK. That is the simplified scenario which we think out. That is, we have remote storage, then we have remote storage connected to IPU, and IPU expose some device to host, which how it is discussed by Yadok. That is, we discuss demo, bare metal demo on Intel IPU, but the IPDK may help with this kind of things that you are able to develop your software without any IPU. So that is proposal. Okay, in IPDK we have some virtual environment based on the SPDK and In this infrastructure, we have some defined receipt how to run this kind of flow. In this version of IPDK, we have initiator flow only, and in this flow we have 3 containers which is connected together. We have nvme-tcp between the storage target and IPU storage container. Then the virtio-blk interface is exposed to host. Key part of this solution that is that if you want to configure IPU and we want to exercise of IPU, we use SMA interface. That is something which Jadon discussed earlier. That is, so if we look on this picture, the SPDK is used everywhere, and is the SMA interface that is the key interface for configuring IPU. Next slide. That is another initiative that is called Open Programmable Infrastructure, that is under a Linux Foundation umbrella. That is some motivation. Okay, we want to have open standard OPI API, which should fit to any devices for any DPU, IPU, to configure infrastructure devices. They have the OPI discuss as well the different use cases. Next slide. And if we look on OPI and IPDK and in storage topic, we have released for IPDK last summer, and we deliver the simple scenario when we have when we expose virtio-blk device to host. We expose we have application running on IPU with SMA, and the remote target is nvme-tcp. Everything is available on GitHub, and that is as well a dedicated Slack channel for storage topic. And OPI, that is another initiative which I mentioned, and the OPI is focusing on defining OPI interface for storage, and that is as well the Slack storage channel. And that is as well some proposal how this kind of API should looks like on OPI GitHub. Next slide. What we have, what we plan to do in OPI and IPDK for storage. First, I would like to say how this kind of project is connected. That is, IPDK is a sub-project of OPI, so that is pretty connect. We have release for IPDK, but we consider to establish releases for OPI as well. That is the plan. And if we think about the storage topic and OPI and the IPDK, we want to expose more use cases. Now we expose just bare metal and virtio-blk use cases, but we consider in the next release to expose NVMe device to host, and we think about to exposing containers and CSI plugin, which will be SMA based. So that is our next step for OPI and IPDK. So next slide, and Jadon, please take over.
Okay, thanks, Yarik. So it's a quick summary. I mean, we talk about IPU, DPU based storage solutions and how SPDK can be really used, right, to enable each usage model. We really think this SPDK is an ideal framework for IPDPU storage solutions. So we also appreciate all the enhancement going to SPDK over the last couple of years, and there will be more enhancements going to SPDK, which will make IPDPU storage solutions better and better. So we highly recommend SPDK for IPDPU storage solutions, which are going to also help eventually the IPDK and OPI projects, which often prefers to the standard-based APIs and the standard-based solution. So it's very important, and we are a strong believer that the SPDK is the ideal framework for IPDP storage solutions. So with that said, we really encourage and welcome to SPDK development and help the integration with the IPDK and the OPI projects as well. That's basically what we have today. We thank you for listening, and thanks for that. Thank you. Bye.
Thank you.